Hi there. In this video we're going to talk about geometry, transformation, and determinants in R3. We're going to explain how to convert a linear function to a matrix, visualize a linear transformation, and relate the determinant of a 3x3 matrix to volume. Let's get started. Consider the following linear function. It takes inputs x, y, z and outputs the following vector. We want to find a matrix that represents this linear transformation T. So what we're going to do is we're going to say this matrix A, when multiplied against the vector x, y, z, has to give us the same output as the function T. And this is going to constrain what the matrix A of T can do. Right? Whatever we put in this big blank matrix has to equal the output of our original linear function. So if we want to get this first row up top, right, we need something that when we multiply against x, y, z gives us x plus 2y. So we're going to put a 1 here, a 2 here, and a 0 here. When we multiply 1, 2, 0 against x, y, z, we get x plus 2y. Similarly, for the next row, when we multiply, we want negative x plus y plus z. So we want negative 1, 1, 1. And for our last row, we want to get 2x plus 3y minus 2z. So we're going to multiply 2, 3, negative 2. So what we're doing is we're taking the coefficients from the right-hand side, pulling them over and putting them into our matrix. Okay? So this gives us a matrix, A of T, that represents the linear transformation T. All right, let's sketch what that looks like. We want to sketch the effect of A of T on the cube with sides E1, E2, and E3. So let's do the matrix multiplication. We get that we're multiplying the matrix against 1, 0, 0. There's a very key point that I want to make here. When we do this matrix multiplication, we're always multiplying rows against this column. And the only non-zero entries we're going to get are when that first number multiplies on here. Okay? The rest of these zeros will cancel everything else out. So we're going to get the whole first column appearing when we multiply by E1. And when we multiply by E2, right, now this coefficient is going to extract information from our second column. So all we'll get when we do the matrix multiplication is the second column. Let's see what happens when we do E3. When we use E3, this last entry is going to extract this column of the matrix for us. And we get this. So there's how we multiply a matrix against an elementary basis vector, or a basis vector. We extract the corresponding column. All right, now let's sketch those three vectors in R3. We get something that looks like this. Sort of odd parallelpiped shape sitting in R3. Okay. Now that we've got this region in R3, we're going to calculate its volume. Okay, we're going to compute the volume of the parallelpiped spanned by these three vectors. And we have a relation that says the volume is equal to the absolute value of the determinant of those three vectors. So if we calculated the determinant, we get negative 5. Taking absolute values, we get 5. Okay, so we're able to take these three vectors in R3, look at the shape they form, and then calculate the volume of that shape. Thanks for watching.